Okay, great. Well, today we will get into chapter 4. Okay, and chapter 4 is all about looking at describing a relationship between two numeric variables. Okay, so the key here is that we are looking at two numeric variables. So both of them have to be numeric. You cannot have one of them being categorical or both of them being categorical. Here we're talking about two numeric variables. Okay. I guess before I go on about today's topic, just in case there were any concerns about the quiz or whatnot, so I'll try to get your quizzes graded and the scores posted by tomorrow. And if you'd like to look at your quiz and see what questions you got wrong, just send me an email and I'll bring your quiz to class the next week. Okay? But please be sure you send me an email and I'll set your quiz aside. Okay? And bring it to class. So that's how it goes. I hold on to the quizzes. Again, I don't let students keep the quizzes, but I feel like the practice quizzes are representative of what the type of questions that are asked on the quiz, and so I don't feel like I'm depriving you of a study resource here. Okay, so let's talk about describing a relationship between two numeric variables. Okay, and so generally what we want to do is we want to we have the goal of trying to see if there's explain a relationship between these two variables. Okay, and so one of the variables we will call x and the other variable we call y. Okay. Okay, and we'll get into more details about this relationship between x and y and all of that. Okay, and so we can take a look at any data set. Okay, any data set where we have gathered at least two variables that are numeric. Okay, so let's say we looked at a bunch of let's say we looked at a certain species of snake. Okay, so a certain snake species, and let's say we, gathered, 10 different snakes or something. Okay. Okay, and for each snake, we are going to record two numeric variables. Okay, so we will look at, we will measure the length of the snake. And we will also measure the weight of the snake. Okay, and so we want to know, is there a relationship between, and so, just arbitrarily, I'm going to call this one x and y. So x will be the length and y will be the weight. And we want to know, so if here's a picture I'm making of a snake. Okay, thank you for appreciating my picture. All right, and so, if we looked at two snakes, all right, and one is longer than the other, okay, and you had to predict which one would weigh more, which one would you say weighs more? The longer one, right? Okay, and so, we expect to see a relationship between the length of a snake and its weight. And that relationship should be, and that would be, in general, snakes that are long will weigh more than snakes that are short. Okay, is that all right with everybody? So let's we'll save that. Okay, and so the tool to kind of visualize this relationship, okay, is the scatter plot. And so the way this will work is, you have x, which is the length, and y, which will be the weight. Okay, and so I don't know. Let's say we have a snake that's 25 centimeters and weighs I don't know, 120 grams, and then a snake that's 30 centimeters, and so this one maybe is 140 grams, and then a snake that's 27 centimeters that weighs 130, and 20 centimeters I don't know, weighs 95 grams. Okay, and so if we put length on this axis and weight on this axis, we would just graph coordinate pairs, right? So we would start off, 16, 17. Now this is going to be a problem. This is where 30 is. Okay, and so I would have to graph each of these things. So 20 is at 95, and so this one is right here at 20, 95. And then, I just go through and I graph each of these. 1, 2, 3, 4, 5. 25 is at 120. And then 30 is at 140. I'm just ballparking these figures. 27 is at 130. Something like that, okay? et cetera, et cetera. Okay, and so if we had, and so you'd have one dot for every observation.
Professor, what's that in
What's what?
those numbers on the left of the table?
These?
Yeah, yep.
What?
Oh,
What? Okay, great. Okay, so you have one dot for every observation, and then so you have, you know, if we have more data points, so I'll just say, you know, more data, but I don't feel like writing all of these. So we'll say more data, and then, you know, I'm just going to kind of make up some dots for what we might have in terms of snake length and weight, okay? Maybe something like this, okay? Just graphing a few things, okay? And then so just looking at kind of the overall trend that that appears, we can say indeed the data supports the notion that snakes with high length generally have high weight. Snakes with low length generally have low weight, okay? And is that statement okay with everybody? Yeah. Okay. Are there any questions? Okay. So then, and this is kind of the idea that we're getting at. We're going to look at different numeric variables, and you just have to keep in mind that each data point represents an observation. Okay, so in this case it was a snake, and each snake has two numbers recorded, or two values associated with it. Okay, we could do the same thing for our classroom, and we could say, we can ask you, you know, how tall are you and how much do you weigh, okay? And so every student here would have two numbers associated. You would have a height and you would have a weight associated. And we can see, is there a relationship between height and weight? Or we can ask any other questions that would be answered numerically, okay? We can say, ask, you know, what is your age and what is your annual income, or things like that, okay? And we can see, is there a relationship between age and annual income? Maybe there is, maybe there isn't, okay? And things like that. So every observation is either a person or a thing, a snake, whatever it might be, okay? Some of the examples in the book are, each observation is a state in our country, okay? So California gets one line, and, you know, you record values associated, you know, for California. So it could be like, in California, the average whatever is this, and the average something else is some other number, okay? And then you go through all 50 states and you record these values, okay? And then we would plot them all, and we would try to discuss what kind of relationship exists between these two numeric values, two numeric variables, okay? So I'll write that down. is an observation. So, you know, maybe perhaps maybe it's a person, you know, an animal or thing, even a state. Okay, and there are two numeric values associated with that observation. Okay, all right, and so when describing a relationship, there are three things you want to talk about. Okay, so one is the direction or trend. Okay, and these will, you use words like positive or negative or neither. Okay, then you also want to talk about the strength. Okay, and the strength can be anywhere from weak to moderate to strong. Okay, and then lastly, we want to talk about the form or shape. And as far as form or shape go, we would use the words linear, or nonlinear to describe the relationship. Okay, so let's talk about each of these things. Okay, so we'll talk about direction first. And we'll talk about positive direction. Okay, so if the direction or the trend is positive, positive means that large values of x are associated with large values of y. Okay, and small values of x, small x goes with small y. Okay. All right, and so your data will look like this. So you have x, okay, and again, you have small x over on this side, and you have large X on this side, right? Because values increase as you move to the right. And over here you have the y-axis, so you have large Y up high and small y down here. And values increase as you go up. And so what you see is that in areas where you have small x, you also have small y. Okay, so you have values in this region indicating small x and small y, whereas over here where you have large X, you also happen to have large Y, okay? All right, and so this should be flat. Okay, and so examples of things that have positive relationship, positive trend or positive direction. Okay, could be, you know, X could be someone's height, and Y could be their arm span. Okay, so you look at how tall someone is, and then how, you know, how far is it from fingertip to fingertip, their arm span. And in general, people who are tall will have large arm spans. People who are short will have shorter arm spans. Okay. Maybe okay. Perhaps you know, if you're looking at sports stuff, okay, it could be you could look at winning percentage of a team, so how often a team wins, and Y could be ticket sales. Okay, and so it's a known thing that when teams are winning a lot, ticket sales for their events go up, okay? And when the team is in a slump and they're constantly losing, so their winning percentage is low, their ticket sales go down, okay? Because in general, people like to see their own teams win, okay? And same with merchandise, things like that, okay? So things go up and down based on how much the team wins and loses, okay? And it's not going to be a perfect relationship, but you're going to have some kind of relationship like that. Okay, so those are examples where you have positive trend. Okay, and then so the flip side would be negative trend. Okay, so negative direction or negative trend. What does this mean? This means large X goes with small y, okay? And small x goes with large y. Okay, again, in general. So the trend for negative direction would look something like this. Okay, and so over here we have large X and small x, and here we have small y and large Y. Okay, and so we see, you know, for small x is associated with large values of y, whereas large values of x go with kind of small values of y. So we can see that. Okay, so examples of negative direction or negative trend. So x could be the number of miles driven on a car. And y will be, you know, resale value. Okay, so in general, if you look at cars that have lots of miles driven on it, they will sell for less money than cars with fewer miles driven on it. So you have stuff like that. Other examples of X and Y having a maybe X will be could also be number of hours spent studying, and Y could be number of hours watching TV. Okay. So, in general, if somebody spends many hours studying, they probably watch fewer hours of TV. And if someone did not had very few hours spent studying, they would have more time left to watch TV. So, of course, it's not going to be, these are not the only two ways to spend your time, so it's not going to be a perfect relationship, but we would probably see some kind of trend like this. Okay. The real question is, is there a negative trend between hours spent watching TV and test scores? Okay, that would be the real question, right? Who knows? Maybe yes, maybe no. Okay, so that's negative direction. Okay, and then you've got neither. So neither positive nor negative. Okay, so something that looks, kind of has a flat trend. Okay, this could be, X could be a number of pizza slices eaten during the week. And then Y could be a number of hours of sleep. Hours of sleep during the week. Okay, and so you're going to have some people that ate 0 slices of pizza, okay? And then you're going to have some people that ate many, many slices of pizza during the week, all right? But in general, if you look at how much sleep someone gets during the week, okay, probably a fairly constant amount, okay? Some people average about 6 hours a day, some people maybe 8 or 9 hours a day, but something somewhere in there, okay? What's that? Must be nice to get 8 or 9 hours, so everyone's different, right? But, you're not going to see people, you shouldn't see people getting 20 hours of sleep a day during the week, and you shouldn't see too many people getting, an average of 4 hours of sleep during the week or something, because, sustained, that would be very bad for your health. So, and as far as how much pizza someone eats, that's subject to debate also. But you're going to see some kind of trend like this, okay? Or maybe you get something that looks like this. Okay, this could be, X could be time after liftoff. And then Y could be altitude. Altitude of some toy rocket or something, okay? And so, in the first half of the rocket's journey, it's positive, okay? With time, it's getting higher and higher up, but then at some point, the direction changes to negative. So the words positive and negative are not enough to summarize the relationship.
Would there be like a name for that? Like if the other one was like flat, trend,
Uh,
or just still?
yeah, you know, at this point we're just talking about positive and negative direction, okay? In a moment we'll talk about linear versus nonlinear. So in our class we're only going to worry about straight line linear relationships, you know, but if in another class you might say this is a quadratic relationship or something like that, but we're not going to worry about that, okay? Okay, so this is neither positive nor negative. So that's the direction. Okay, so you know, let's see what you guys think here. Okay, so let's say x is the altitude of a city, and y is the air pressure. Okay, is this going to have a positive, negative, or neither? Oh, maybe you guys don't know. Take your science classes. You guys didn't learn this in science?
That was like years ago, general ed.
Okay, well, all right. So Colorado is high up. What do they say about Colorado? Do you guys? Okay, yeah, it's a mile high city, meaning it's high up. But then, what do they say anything about the air? Is it easier to breathe, harder to breathe? It's harder to breathe because the air is thinner. Okay, so you're gonna have lower air pressure. So you know, Colorado, or I should say Denver. Okay. You know, high altitude, so high X, air pressure low Y. Okay, so this would be an example of negative trend, right? So negative trend. Okay. Let's see. Okay, so we'll say X will be outside temperature. And Y will be ice cream sales.
Positive trend.
Okay, so what do you guys think? Positive? So, positive, negative, neither? Okay, so on hot days, so that will be high X. Are we going to have lots of ice cream sales or less ice cream sales? Or the same? Probably more, right? So we would expect more sales of ice cream. So that will be high Y, right? Okay. Now it doesn't, you know, we live in Los Angeles, so we don't really experience this. But if it were snowing outside, you know, would the ice cream man be driving his truck around? Probably not. Okay, probably not. So you know, on a cold day, we would probably have low sales. So this will be a positive trend. Okay. I hope we get the idea here. You're gonna take a picture of this? Okay. You know, I post the slides online as well too. Okay. All right. No problem. No problem. Just want to make sure you guys know that I'm posting these things online as well. Okay. All right. So let's just talk about direction. We also want to talk about strength of a relationship. Okay. Okay. So the strength of a relationship, we would either say is weak or strong, okay? So weak, moderate, or strong. So let's start off with strong, okay? So a strong relationship, so if we had a positive relationship, it would mean that you have a kind of this trend where you have very little scatter in terms of the dots. Okay, you can kind of lay a thin pencil down and cover up all the dots. Okay, so you'd have little scatter in the plot. Okay, there's the quote-unquote pencil test, where you can lay a thin pencil down and it will cover up all of the points. Okay, so you have little scatter in the plot. So so that would be a strong relationship. Okay, kind of a benefit of this would be if we are given a certain value of x, we can make very good predictions of y. Okay, and so for example, if I said x is right here, you could go up to here and you could say, okay, well, I would predict that y is going to be, in this zone. Okay, and so that would be a strong relationship. So things that would have, I would imagine the relationship between the length of a snake and its weight. For at least a certain species of snake, I expect there to be a strong relationship. If you are yeah, or even some other examples could be, if you were, I don't know, recording, I don't know, the time it takes to complete something, okay? It could be just, let's say you were baking, or I don't know, folding little crafts or something, okay? And we said, how many craft objects do you have to complete and how long will it take? I expect there to be a strong relationship, right? If you had to make 10 one day and it took you an hour, and somebody said you had to make 20 the next day, we would assume it would take about twice as long, right? 2 hours. And so so we would expect a strong relationship. Okay, anytime if you think you can make good predictions about y based on x, that's going to be an indicator of a strong relationship. Okay. So for a weak relationship, there's going to be much more scatter. All right, so you'd have maybe still overall a positive trend, but something like this. Okay, so here, we couldn't lay a skinny pencil down and hope to cover up all the points, right? Because the thin pencil would only cover the lines in the middle. Okay, so we'd have more scatter, and our predictions of y based on given a certain x will not be as good. Okay, so if we look at x here, you know, our predictions for y will have to be within a much wider zone, right? Okay, so all right. Okay, let's talk about the last aspect of describing a relationship, and that will be the form of a relationship. Okay, so form can either be linear or nonlinear. So linear means that a straight line can summarize the relationship. Okay, and nonlinear means a straight line does not work. Okay, yes?
So does this mean on the scatter chart, you put a line where the direction is? If it matches, that means it's linear?
Well, so maybe I'll draw a few examples, and I hope this will answer your question. Okay, so this would be an example of a linear relationship because it looks like a straight line could kind of describe the relationship between x and y. Okay, so this is linear. Even with lots of scatter, we could still say that overall the relationship fits kind of a straight line trend. Okay, so in both of these, you know, I think we would say, you know, we could have a between x and y. Okay, so this would also be linear. But as soon as you have, you know, some curvature showing up, then we would say it's no longer linear. Okay, so if you have this would be nonlinear because a straight line doesn't really work anymore, right? So because, you know, if I tried to use a straight line, it would look like this, or it would look like this. Straight line doesn't work. Okay, so for something like this, you would need a curved line that goes like this, or something like that. Okay, so this would be a nonlinear thing. You know, or you could have also nonlinear would be anything that kind of rises and falls, or something like this. This would also be nonlinear because a straight line doesn't work for these. Okay, and the only way we can really tell if something is linear or not is we've got to create a scatter plot and look at it. Okay, so to decide if something is linear or not linear, we create a scatter plot and look. that's how we decide if it's linear or not. Okay, so we have direction, positive or negative. We have strength, being strong or weak, and then we have linear or nonlinear. Okay, so in our class, we're only going to deal with linear relationships. If things don't fit a straight line, we're just going to say it's nonlinear, and we're not going to learn how to deal with those things. Okay, so your first step should always be to create a scatter plot, or see if a scatter plot has been made, and to then decide if a linear relationship is appropriate. Okay, so your first step should always be to make a scatter plot or look at the scatter plot. And then decide if a linear relationship works. Okay, so you just want to take a look and say, does it look like a straight line can summarize? And if so, then you can continue on. And it's okay if there's lots of scatter. You can still have a linear relationship with lots of scatter. It's just you'd be concerned if there was some kind of extreme curvature or something to indicate that a straight line is not appropriate. Okay, and yeah.
Can an abnormal thing change it from being linear? Like say if there's one dot that's out of the area?
So if it's just like one outlier, then it's probably okay, and you'd want to take that into account. But we'll talk about that, okay? All right. So we have a numeric summary or a summary statistic that summarizes the direction and strength of a relationship, okay? So we have, and this is called the correlation coefficient. Okay, so the correlation, okay, or the full name is correlation coefficient. Okay. Is a numeric summary or sample statistic that tells us the direction and strength of a relationship between two numeric variables. Okay, and the symbol for correlation is the letter R. Okay, R like relationship. Okay, and I'll talk about the interpretations of correlation. Only make sense for linear relationships. Okay, you can correlation can be calculated for any set two numeric variables, but the interpretations only make sense if the relationship is linear. Okay. So all we're doing is we're just, you know, we said when you describe a relationship, you want to talk about the direction and the strength and the form. We're going to say, okay, if the form is linear, we have this statistic R that will give us the direction and strength. Okay, so once we create a plot and say, oh, this thing is linear, then we can just use R to describe the other two parts, the direction and the strength. Okay, do you guys have this all written down? Okay, so some properties of R. Okay, so R can be any value, or can only be values between -1 and 1 inclusive. Okay. The sign of R is the direction of the relationship. Okay, so for example, if R is positive, then the relationship has positive direction. Okay. And then basically the magnitude of R tells us the strength. Okay, so that is to say, if R is far from 0, so, you know, close to 1 or close to -1, then the strength is strong. And if R is close to 0, then the strength is weak. Okay. R will not tell us if the relationship itself is linear or not. Okay. The only exception is if R happens to equal 1 or happens to equal -1, then you have a linear relationship. Okay. For any other value of R, you can't tell if it's linear or not, even if R is 0.99. Okay. Even if R is 0.99, you can still have a nonlinear relationship. So R won't tell you if it's linear or not. Okay, unless it's equal to 1 or -1. Okay, so let me just kind of show you some examples from, I think the book will do so where's my okay. All right, so let me so we'll copy a few of these into my notes here. So where Where's my snipping tool? Okay, so here we have, can you guys see this? Okay, so here r is equal to 1. We have a perfectly straight line. The strength is strong. Okay, so perfect strength, perfectly strong. Okay, and it's positive direction. What is x? X is a person's height in inches. Okay, and then y is the same person's height measured in centimeters. Okay, so if we think back to, what is kind of the definition of a strong relationship? It's, how well can you make predictions of how good are your predictions of y if I give you a value of x, okay? And in this case, if y is the person's height in centimeters, and I tell you the person's height in inches, can you make a pretty good prediction for y? Yeah, all you do is you just plug in the height in inches into just some conversion thing, okay? You just say what, 2.2 centimeters, I don't know, something centimeters per inch, and there you go. Okay, so your predictions will actually be perfect for y based on x. Okay, so your predictions of y will be based on x will be perfect. Okay, so in this case, you have r equal to 1. Okay, and so here we have another example of a very strong correlation, but it's not as strong as it's not a perfect thing, but it's still very good. Okay, so here we're looking at different probably different countries here. So maybe we look at we're looking at different countries. Our correlation is 0.98, so we see a very strong relationship here. And what we do is we're looking at the life expectancy for men, and we're looking at the life expectancy for women. So, so if a country has poor life expectancy for the men, we're also anticipating it to have poor life expectancy for the women. And if a country has very good life expectancy for the men, we're also expecting it to have very good life expectancy for the women, and things like that, okay? The predictions are not as perfect, okay? So, here are several countries where the life expectancy for men is maybe like 60 years, and then you have a little bit of range in terms of the life expectancy for women, but it's all within kind of just a few years of each other. So here you've got r equal to 0.98. Is this okay? All right, and then and you can kind of see as the scatter gets more and more. Okay, so here is so here the relationship is much weaker. So overall, maybe there's still a positive, maybe still a slightly positive relationship. but you know, lots and lots of scatter, right? So here, you know, your R is only 0.19. Okay, and here we're looking at someone's GPA and the math SAT score, okay? So you have people with very high GPAs getting high math SATs, but you also have people with fairly high GPAs that are not doing super great on the math SAT, okay? So there's still some kind of positive relationship because maybe overall you're getting some kind of trend like this, but your predictive power is a lot weaker, okay? And then finally, if we take a look at this this last one, we see there's no relationship between X and Y here.
So would you say that that's non-linear at that point?
This one?
Equal to zero?
You know, so wait, when it gets to 0? Yeah, at 0 we would say there's no trend, so it really doesn't even make sense to say whether it's linear or not linear, okay? I mean, we just say, you know, no trend, neither positive nor negative. Okay, I mean, you could, whether it's linear or not doesn't really matter. I guess in our class we said we're only concerning ourselves with linear relationships, but we can still talk about when there's no trend, okay? So I'm actually not entirely sure what graph F represents. Oh, okay, this was how long it took someone to complete the marathon, and we're looking at age, okay? So X is age of runner, and Y was marathon completion time. And I guess this was like a recreational one, so not like a kind of like a recreational marathon. Not Olympic competition or something, okay? So you have people of all, you know, wide range of ages competing, or not competing, just running, and then you have people finishing quickly and finishing slowly, and it doesn't really seem to be related to age, okay? Because you got 30-something-year-olds taking very little time, and 30-year-olds taking lots of time. You got 50-year-olds taking little time, and 50-year-olds taking lots of time. So overall, no trend. Okay, and so here correlation is 0. Okay. Yes.
Is the correlation always told?
Is the correlation
Always told, and we have to figure
okay? So the correlation is the result of this formula that we are not going to learn in this class. So as far as this class goes, I will always provide the correlation to you, okay? But you know, maybe in another class you might be given the data and you would have to plug it into the computer, and the computer would give back a correlation. Almost no one calculates correlation by hand using the old-fashioned formula, just because it's a very tedious process. So it could be done, but it's not done frequently by hand. Okay, in our class we learned how to calculate the standard deviation, and we learned the definition of the standard deviation. But you know, if you had 100 numbers in your data set, calculating the standard deviation would be very tedious to calculate. Even the mean of 100 numbers by hand would be rather tedious to calculate, and the correlation is just even worse. Okay, so I won't make you do it by hand. Okay, but you are responsible for knowing the interpretation of the correlation. So here, these were all examples of positive correlation, and then so here are examples of negative, and you can see starting at R is 0, And then as r gets gradually more and more negative, we can see that there becomes less and less spread, or less and less scatter in the graph until you get kind of this perfect, almost a, this perfectly straight line. So here r is negative 0.9, and we see, less scatter than the graphs over here. Okay. Is that okay? So how r works there? Okay, so then why don't we take a short break here, and we'll come back and we'll finish up chapter